Okay, a very good evening to all of you. In this particular session, we are going to discuss about the week 2 content, the doubt regarding that, and the numericals and all with respect to the week 2 assignments so that you can solve it. Okay, so these are the list of the things that has been covered in the. These are the list of the topics that's been covered in the list group 2. I mean week 2. Okay, so let's focus on this particular topics. So the things which we are covered are Miller indices for the plane. It was missing. So last week, that is week 1, we only discussed about the Miller indices for the directions. The plane is missing here. Then the next thing is the line of intersection between the two planes. So we have learned that in the lecture that the line of intersection between any two planes we can find by the two methods. Okay, one is a geometrical method and another one is nothing but a Weiss Zone Law. Well, that is a algebraic method, one of the application of the Weiss Zone Law. Okay, these are the thing that this is one of the topic which has been covered yet. Okay, and then we discuss about the plane normal of a plane for a cubic system. Okay, so for a given plane, what is the normal for the given cubic system? That is a one derivation. We say that h, k, and l for the direction for the plane of the cubic will be perpendicular to the direction h, k, and l. This is the one which been taught in the video lectures. Okay, and after that we discuss about the professor discuss about the Weiss law. Okay, from the diffraction condition, the Weiss law is very useful, but limiting to our what we can say to our syllabus to our content of the video, we can say that the Weiss law we are mostly using for the calculation for the line of intersection between the two planes. Okay, apart from that, we discuss about the coordinate transformation matrix. Okay, how we can transform from one coordinate system to the another coordinate system, and if any position is given in to us in one of the coordinate system, how we can convert it to the how we can find the coordinate of that particular basis, that particular point or that particular vector in the new coordinate system. Okay, so that is the coordinate transformation matrix. Next, we discuss about the reciprocal lattice. Okay, so combining all of these things, we are going to solve numericals based on all this stuff, and so that the assignment question, we will be able to answer it. Okay, so few things I would like to tell you is that the recording of this particular session will already be available. So if you are not available on the particular time, you can always revisit to it. The link will be provided to you on the uh, Swayam portal, and the link the entire video, the entire recording will also be available on the YouTube channel. Okay, and the link of that particular channel will also be provided to you by a mail. Okay, okay, so let's get started with this particular session, and we are going to discuss few numericals. Okay, let's go with the first numerical. See, we are not going to solve the questions which is exactly in the assignments, but we can practice few questions in such a way that we are able to solve those questions. And I'm not allowed to solve the question from the assignments, but we can do some similar type of questions. Okay, apart from the doubt solving, apart from these questions and all, if you have any doubt regarding the any videos, that is any lecture that has been covered by the Professor Rajesh Prasad, then we can also discuss those things. Okay, we'll discuss those things at the end, if there is any question left, if there is any doubt left from the videos. Okay, so let's get started. I will switch off my video so that we should have a good quality. Yeah. Okay, so here we can discuss that. We can see that the question is asking us to find the Miller indices for all the planes. Okay, so we need to find the Miller indices. Here we can see this is a two-dimensional lattice only, right? It's one of the two-dimensional lattice, and the A is in this particular direction. So the A direction has been given to us, A vector, basis vector, and the B is also given to us. Okay, so this is the basis vector is given to us. We can see that this is nothing but a square lattice. Okay, we can select one particular unit cell, and once we start translating it, okay, then in that case the entire lattice will be covered. Okay, let's go with the, we need to find the Miller indices for this particular planes. Let's go with the plane A. Okay, how we can find it? For the Miller indices, we need to find the Miller indices, right? We know that Miller indices can be found only if we know the intersection of the particular planes with the unit cell. Okay, so first thing what we need to do right now in this particular plane is to find the unit cell. Okay, let's go with the this particular, I am drawing one unit cell over here. Okay, so this unit cell I have drawn it. Okay, so now here we can see that this is a direction and this is a B direction. This plane, we can see this plane is cutting our unit cell in two parts, in 2 points over here. One is over here, one is over here, and the second one is over here, right? We know this particular distance, that is along the x direction, we can see the distance is nothing but y. In the y direction, we know this is nothing but a 1 by 2, 1 by 2 times of b, so we can say that this is a b by 2. And in the c direction, we know since it is a 2D lattice, it's going to be parallel to the CA. Okay, so it will be 0 times, sorry, infinite times c. Once we find this, once we find what is the value associated with each lattice, each basis vector, what we can do, we will just take its what we can say, we will just take its number, that is 1. We have 1 by 2, and then we have infinite. The step number, last step will be to take the reciprocal of it. Okay, whenever we talk about the for the plane, we need to take the reciprocal. In the direction, it was not the case, right? So once we take the reciprocal, what we will get? We will get 1. Inverse reciprocal of 1 will be 1. 1 by 2 will be nothing but 2. And the infinite will be 0. Okay. So this will be the Miller indices for our plane A, set of plane A. Okay. What about this plane? Let us take some another plane. Plane B we are talking about. There is no change in the, just a minute guys. Yeah. There is no change in the B. Okay. Like there is no difference between A and B. The method which we will follow will be the exactly same. Okay. So here again we are going to make a unit cell. Right. Let's make a unit cell. I will make with the red color. Since we know this is a square lattice, we will make a square unit cell only. So this is what we are making. Okay, this is a unit cell which we have. Now, if I take this particular plane, where should I take the origin? Okay, if I take this particular origin, if I take this particular lattice point to be my origin, this particular lattice point to be my origin, then what will happen? The plane will pass through the origin, which cannot be. By the convention, by the method, we have already learned that we will choose the origin in such a way that it should not pass to the origin. The plane should not pass through it. So we are left with the 2 points. Okay, we are left with the multiple points, but we will for this particular unit cell we will select this point. Let us say this particular point. One can also select this particular point. There is a note. There won't be any difference in the answer obtained, but still, let's go with the first one. Okay, we know that A lattice is along this. Sorry, A basis vector is along this, and B basis vector is along this. Okay, considering this to be the origin, what we know in the A direction where it is cutting, this particular plane is cutting at 1 of A. So we can write the 1 of A. What about B? Where does it cutting at the B? We know that it is cutting in the negative direction of B. Okay, so we need to go negative of B, that is minus of B. And for the C, we know it will cut at the infinite times of C. So now we got to know that the indices, the value associated with each basis where it is cutting. Okay, so now what we can take, we'll take one, we'll take a value associated with them, that is 1 over here, that is -1 over here, and that is infinite over here, right? Now what we will do, we'll just take the inverse of them, and the obtained value will be 1. Again, the inverse of 1 will be 1 only, -1 will be -1 only, but infinite will be 0. And this is our plane. We will enclose them in this bracket. Okay, and that's how we solve the part A and the part B. Okay, and we find the Miller indices. In the similar manner, what we can do, we can go for the C also. Let us say this is our C matrix. Sorry, this is our C. Okay, so we need to again we will follow the same procedure. So you guys can also solve with me, and you can unmute yourself if you want to answer. Okay, before, and you can also answer in the chat box. Okay, so let's get started with the C. C is the easiest one, but sometimes people find it to be the complicated. We'll again go with the same manner that we are selecting a unit cell. Let us say we are selecting this particular unit cell. Okay, we can see that this particular plane, if I take this particular, let us say this, we are talking about this plane, and we are taking this to be the origin. Since our if I take here to be the origin, then our plane will pass through the origin, and that shouldn't be the case over here. Okay, so let's take this particular origin, and what we can do, we can know that this is a and this is a B. Okay, and so where it is cutting at the A, it is not cutting at the A, it will cut to the A, that is this direction, at the infinite. This plane will cut A at the infinite, so we'll write the infinite times of A. What about B? Will it cut to the B? Let us say we are going to the B in B direction. So from this particular point, if I draw, yeah, it will cut to the B, but it will be in the negative of B, right? So we have to go in the negative direction, considering this to be considering the upward direction to be the B, which is given in the question. Okay, so we need to go in the negative direction of B, that is minus of B, and we know for the C that it is nothing but infinite times of C. Okay, so let's take we got the value that is infinite minus of 1 and again the infinite value. Okay, we can take the reciprocal, we'll get 0, we'll get -1, and again we'll get 0, and this is the Miller indices for the plane which is parallel. Okay, in the similar manner, one can solve, I'm not going to solve this, but one can solve for the D also, and one can solve for the E also. Okay, at least let's finish this particular thing with the E. Okay, again we need to find, I'm not going to solve for the D, let's solve for the E part. Since all of them are similar, we'll go with the last one. So let's select in this particular plane, the plane corresponding to this, the set of planes, we can select a unit cell. Unit cell will be again the square lattice only. Will made by the square lattice. Now, what we can see over here is that this plane will again mark our A axis and B vector. Basis vector will first mark them, and we know this is a plane. Let us consider this particular plane. Okay, that is this one. Okay, so it is intersecting our unit cell at this particular point, at point over here, and it is intersecting at point over here. So we cannot choose our origin to this particular lattice point. We'll choose it somewhere over else. Let us say we are taking it over here. Okay, so in this case, what is happening that I shouldn't have drawn this over here. This is our A. Okay, so now what we can see over here is that this entire plane, this plane which is passing, where it is cut, it will cut at the A. It is cutting A at the distance of 1 by 2. So we will write 1 by 2 times of A. What about B? Again, B is in the upward direction, and we can see that the plane is cutting to the in the downward side, and by the amount of unit. Okay, this is a point. If we consider this particular point, so we know that this is nothing but a unity. So it will be B 1 times of B, and the infinite times of C. In C direction, it won't cut. Okay, so we got the values. The values which we got, they are the values which we got. They are 1 by 2, 1, and infinite. Right? We'll take the reciprocal of it, that is 2. We'll get 1. In reciprocal of 1 will be 1, and infinite will be 0. In this manner, sorry, I missed something. Yeah, sorry. The B will be nothing but it will be minus of B. Okay, so it will be minus of 1, and it will be minus 1 over here again. Okay, so this is something which we got. We don't write minus usually in the when we represent in the Miller indices. We'll write in the terms of bar, 2 1 bar 0. Okay, let's see if there is any comment. Yeah, there is no. Okay, so that's how we solve this particular question. That is a question number A, where we need to find the Miller indices corresponding to the each set of the planes. Okay, it's easy only. All we need to know the direction of the Miller indices. Sorry, the direction of the basis vector, and similarly we can select the unit cell corresponding to the each set of planes. Once we did that, all we need to do, we need to find the how they are intersecting, and we will be careful that we should select a point, that is we should select the origin in such a manner that it shouldn't intersect with our plane. Okay, and that was the question number 1. Let me know if there is any doubt in question number 1 before we get to the question number 2. Okay, seems like there is.
No, go ahead.
So we'll proceed to the question number 2. Okay, so what question is telling us? The question is asking us, let me read if it is not visible properly. Yeah, the question is asking us, consider a tetragonal unit cell. Okay, tetragonal, we know that is where A and B, the lattice parameter A and B are equal with each other, and all the this we can say angles, interaxial angle between them will be 90 degree with each other. Later on, we will understand that this is not the defining factor for something to be the unit cell to be the tetragonal. But for the time being, let's stick. And here it is also giving that the values are in such a way that it is a 2 2, that is A and B are equal, and C is different from each other, different from 2. Okay, and all the angles are 90 degree. Okay, so now what we need to do, we have to sketch the unit cell to a scale, that is it should be 2:3, that C axis should be 3 and the A axis should be 2, A and B should be 2, and draw the outline of the 111, 120, and 1 bar 31. Okay, so we need to draw this particular set of planes. Okay, since it is represented in the this type of bracket, what we can say, it is not a family of plane, it is a single plane, right? The family of plane will be represented in this particular brackets. Okay, so let's get started with this particular question, what we need to do over here. So I will take a scale properly so that we are stick with the questions what they are asking, that is they want us to be in the 2:3. So let's select a tetragonal unit cell. You guys can also solve with me. It won't be 100% perfect since we are restricted, the paper is restricting us to be in the 2 dimension only. Okay, so let's draw it. So this is our tetragonal unit cell. I will check if I have some other color so that we can. Okay, yeah, I have blue also. Okay, yeah. So now let's go with the first question. Uh, uh, First of all, let us mark the axis, the basis vector A, B, and this will be C. Okay, so let's mark them. That is, first we will mark 1, 1, 1, this particular plane. Since we know all of them are positive, we can select our origin to be this particular point. Okay, let us select this to be the origin for the case 1, the first case. What we know here is that this particular plane 1, 1, 1, it will cut our unit cell in a unity at the at A, in A direction it will cut at the 1A. Even if you take the reciprocal, if you are saying that okay, since we took the reciprocal last time, we should take the reciprocal here also, you are right. We need to take the reciprocal of it, but reciprocal of 1, 1, 1 will be nothing but 1, 1, 1 only. Okay, now we know that this plane will be cutting the a-axis by the unity at the unit distance. Okay, so this will be the one of the point which we need to consider. In the b direction, again it will cut by the unit amount, that is, let us say over here, and in the c direction again it will cut over here in the unit amount. So now we need to draw this particular, we just need to connect these particular points easily and it can be drawn. That's how easy it was. And this is a plane. The first part is over. Like among the first parts, first A will be over. Let's go with the second type. The second one is asking us, this time I will choose some other color. Yeah, it will work. Let's hope it will work. So now we are having 1, 2, 0, this particular plane. Okay. So now, again, this is the Miller indices for the given plane. We know that we need to take the reciprocal of it first. Reciprocal of 1 will be 1. Right. Reciprocal of 2 will be 1 by 2. Better we take black only. And reciprocal of 0 will be infinity. Okay. So at this particular unit basis vector, okay, 1 times of A, 1 by 2 times of B, and infinite times of C. That is, it will not cut the C axis. It will cut the A axis at unit. That is only over here only. That the first particular point. Okay. So let's me mark something like, yeah, this particular point in the B direction. We know it will cut by the 1 by 2. So this is entire B. So we can say that this will be nothing but this will be the point where our this particular 1 by 2 will lie. And in C we know it will not cut. So what we can do, we need to draw this particular unit cell and it should be parallel to the C axis. Okay. So let's make it parallel to the C axis. This is how it will go and this is how it will go. Okay. So our next plane is this one. And that's how it is. Okay, let's connect this also. So this is our next plane. Okay, and that's how we solve this particular question number 120. Let's go with the third one, that is a 1 bar 3 1. It will be little complicated, but still we can draw. Instead of drawing over here, we can select some other. Let me take another page. We need to know that 1 bar 3 1 we need to plot. Okay. So 1 bar 3 1. Again, we need to draw a tetragonal unit cell first. This time, even if I am not sticking with the particular scale, it's okay, right? Since we are only doing it in the manual way. We are not sticking with the number right now. whether we stick or not for this particular type of questions is doesn't matter. So it is saying that 2 is to 3 ratio. I'm not maintaining it, even though I know that in the exam, if they ask and they are providing us the scale or the graph paper, then we can draw it in the particular manner. Okay. Okay, that also remind me that I can choose the graph paper from next time onwards. So this is our unit cells. Okay. Okay. Since here we can see that the first part, the first Miller indices is in the negative. So what we know is that the a-axis will be shifted. The origin will be shifted in the a direction. Okay. So we can select our origin somewhere over here. Let us say this is our origin. Okay. Since it is not negative in any other of the direction, we are not shifting in the direction of B, in the direction of B, and in the direction of C. We only shifted the entire thing in the direction of A, because the A term, the first value of the Miller indices was negative. So now we can do it. All we need is we know that this is cutting at the 1 bar 3 1. That is minus 1 3 1. The Miller indices is minus 1 3 1. It's not cutting at the 1 bar 3 1. Sorry for that. This is the Miller indices as minus 1 3 1. Okay. Now we will take the reciprocal of it. That is 1 by 3. That is minus of 1. That is a 1 by 3, and this is 1. Okay. Now one can say that okay, I don't like fraction. I would like to multiply by the 3 to all of them. But in order for us to do this, if someone want to plot this, they will need 3 unit cells. So we need to extend 2 more unit cells to it, which I am not going to do. It's already hectic for me to draw one only. Let's stick with this. That is a minus of 1, 1 over 3, and 1. Okay, we are sticking with this one. So we know, considering this to be the origin at the in a direction, it will cut at the minus of 1. So the first point we obtained over here. This is our first point. In the B, it is cutting at the 1 by 3. Okay, considering this to be our origin, our axis will lie over here. Pardon for me to draw over here. I was just representing the direction. Okay. So our B, this is the C, and this will be the B. We know B is our this particular plane will cut B at the 1 by 3. So let us say somewhere over here, like manually we can select, not worrying about the exact value, but yeah, we can say that this is a point where the plane is cutting. Okay, and in the C direction, it is cutting at the 1. That is, it will consume this entire length. So somewhere over here, we got 3 points. That was all we needed. Now we can join them, and our plane is ready. It's look like very small, but yeah, this is a plane. If you look from the one of the direction, it will look something like a triangle to you. Okay, and that's how we solve this particular question. 1 bar 3 1. Okay, I hope it is easy. It's very easy. So now let's get back to our question. That is, the first part is over. Now we need to go to the second part of it. Now what second part is telling us? It's asking us to draw on a new sketch. Okay, we have to draw a new sketch now. We have to draw all the members of 110 family. See, it is represented in the curly brackets. That is, it is written as 110. So this is a family. We will represent this particular family. We will draw this particular family in one of the color, and the member of the other, that is a 0 1 1. This is another set of family of planes in another color. Okay, we'll draw this particular, let us say, in the blue, and we'll draw this in the black. both were BB only. Okay. See, if this would be the what we can say, if our unit cell, sorry, yeah, if our unit cell would have been cubic, so this both will be corresponding to the one family, one of the family, only one family. In the case of cubic, we will write this entire thing over here in this particular manner only, and it will consume this particular set of family also. But in the case of tetragonal, due to the unsymmetry created by the c-axis, which is expanded, or we can say contracted, elongated or contracted in the c direction, the symmetry got disturbed, and due to that, our this 110 and 011, these are the two different set of family of planes. Let's start with the first one, that is a 110. Okay, let me choose another paper. Pardon for this camera, it's not quite that good, but I've ordered it. It will take some time. Okay, so we need to draw this 110 set of family of planes in the tetragonal unit cell. Okay, so let's draw a tetragonal unit cell again. I hope you guys are with me only. You can also try on your end. Yeah. Okay, so yeah, since I got the response, I think yeah, I'm audible and yeah, perfect. Okay. And if you have any question now, if you want to ask any doubt, you can always unmute yourself. Let me see whether I think I might have given all are muted. Is it? Uh, can you guys unmute yourself? Is it possible for you, or the access has not been given? You can let me know in the
Oh,
chat box.
I'm audible. Hello, hello, Vikas.
I'm not able to hear anyone.
Hello,
Okay, I think you guys can.
hello,
You are able to, but I'm
hello,
not able to hear any voice from your side. So please
hello.
always use. You can always use the chat box. I think there is some technical issue over here. Okay. Okay, let's draw this particular unit cell. It's not looking like it's little disturbed, like the base is little elongated, but still we can consider this to be the unit cell of the tetragonal. Okay, now let's move that we need to draw them. First of all, let us see in this particular direction what 110. We'll consider this particular plane 110. We can also write the 1 bar 0, this to be another plane. Considering 0 to be over here in this particular fixed axis, that is C, we are not going to move the 0. We can also write 1 bar 0, like negative to all of them. And here again, if we apply negative to all of them, we'll get 1 bar 1 0 to us. Okay. And this is how it is. So this is a plane. Let's draw the first plane. And this is our A axis. This is our B axis. And this is a C axis. Let me note the time. 35. Okay, it's good. Then this is how it is. Okay. Let's draw first one. That is, it is cutting A at the 1, B at the 1 and 0. C at the 0. Quickly we can know that yeah, this will be nothing but this. And C at the 0 means, sorry, it's not cutting C at 0. It is cutting C at infinity. Oh, I think there is some issue with the audio. Okay, let me see if there is anything I can do on my end. Uh, uh, Turn on their video, turn on their mic. Your is fine, sorry, it's from our side. Oh, okay, I thought it's from my end. Okay, you can always refresh it and your page, and it might be possible. Sometime it happen. Okay, so now let's go with this particular. So now we know that this will cut, this particular plane will cut at the infinity to the c-axis. Okay, so we have to draw a parallel. Okay, we can take this, we can join these two things, and we can make them parallel to each other. We just need to extend them. Where they end on the upper side, we'll join it. So this particular plane is 1 1 0. If you try to draw 1 1 bar 0, let us try to draw 1 1 bar 0. In the y direction, sorry, in the b axis it is negative. The Miller indices with respect to the b is negative. So we need to shift our origin. We cannot sit at this particular origin itself. We need to shift to the other point. Okay. So in this way, what we can say is that our origin will lie over here. So this will be our origin for the second case. This case is 1 1 bar 0. For this particular thing, for this particular plane, we are choosing this particular origin. Okay. Again, we can see that since our origin over here, this will be the B, this will be the A in this case, and this will be the C in this particular case. Okay. The axis will remain as it is. It will remain at their same orientation. We are not going to change them. Okay. So now let's go ahead. At the A, it will cut by the unit amount, that is 1. That is 1 over here in this particular direction. Okay. In the B, it will cut at the -1. In the B direction, it will cut -1. So we can say, since this was our origin, we have to go back. So this is the case. So we got this is the second point. Instead of circular, I should mark the square so that it's differentiating from the first one. And in the C, it is cutting the C axis at the infinity since it is 0. So now what we can do, we just need to take a parallel to this thing since it is not cutting. Okay, and now we can join them. And this is how this first and second plane we have drawn. Okay, this particular third plane, let's talk about the third plane. 1 bar 1 bar 1 bar 0. This will be parallel to the 1 1 0, right? So what we can say, this will just coincide with the 1 1 0 plane. Let's prove it whether what we are thinking, whether it will coincide with the 1 1 1, sorry, 1 1 0 or not. Okay, so what we can do, in this case 1 1 0, 1 bar 1 bar 0, we need to change our origin in both the cases, that is A also and in the B also. Okay, let us consider this was the origin and we are shifting in the A direction over here, and in the B direction also we are shifting, so our new origin will be over here. So let me mark it. So this is our origin. We are selecting this in the case for the case of 1 bar 1 bar 0. Okay, so considering this to be the origin, this particular thing to be the origin, this particular point to be the origin, we have to mark 1 bar. That is, if I take the reciprocal of it, I will get 1 bar, and infinity. So it is cutting A axis at the minus of 1. So I have to go in the negative direction of A. So this is the A direction. This is the A direction. So I will go in the negative of this. So this is the point I will get. And what about the B? In the B direction also, we can say that, okay, this is the B direction. Since this is the origin, this is our v direction, and we need to go to the negative of this, that is at this particular point. And the c direction, it is infinity. So again, we got the same point which with respect to the 110. Let's draw it. We can see that it is going to coincide with the 110, and this is how it is, right? This is the 110 plane. So if I take any plane and I make a negative of it, like just negative in all the direction, that is a 110, it will be 1 bar 1 bar 0. 1 bar 0 will be 1 bar 1 0. So now what we need to do, we don't even need to draw this 1 bar 1 0, since we know it will coincide with 1 bar 0, and 1 bar 0 was this particular set of plane, sorry, this particular plane, not the set, this is only one. So on this particular plane, our 1 bar 0 will lie, also our 1 bar 1 0 will lie, and for this particular, here we have already shown that 1 1 0 will lie and 1 bar 0 will lie. Okay, and that's how we solve the first part of it. In the similar manner, we can go for the second part also, that is nothing but 0 1 1, this particular thing. Okay, so, let's try to just I'm leaving it to you to solve this particular case. This is exactly similar with this particular case which we have drawn, but let us try to make how many planes will be there. Before I leave it to you, let us try to make how many planes will be there associated with the 0 1 1. Okay, let's take a fresh page. Zero, 1 1. Okay, so what we can see, what we can do over here, we can apply, we can take first plane to be 0 1 1. We can take a negative of all of them, 0 1 bar 1 bar. Let's take a negative of other plane, only one direction will take a negative, and now we'll apply the negative to all of them, 0 1 1 bar. Okay, now let's take the negative to the other one. Okay, so now here we can apply negative to all of them, and we'll get 0 1 bar 1. These both are equal, these both are same, so we can neglect it. All we need to do is draw this. Okay, and yeah, so these are the things which we can draw, and it is very easy, it's not that difficult. Okay, so you can draw it. With that, our third question is over. Okay, we can sketch them, we can draw the plane. We have already marked a few planes, that is part A, and second we deal with the family of the plane. Okay, and this is how it is. Now let's go to the question number 3. So first two questions we have solved. This is our question number 3. So okay, so there is a Miller indices of the blue and red. Instead of red, let me mark the black. I don't have red color right now. I will take a blue and black. I should have write black with the black also. Okay, we need to find the Miller indices of the blue and red planes. They are the two planes associated with it over here. Let's take the first one, this particular to be the black one. And the second one we can take to be the blue. Okay, these are the two planes which is given to us. what we need to do, we need to find the Miller indices of the blue and red plane. It is very easy. Exactly what we did in the first question and the second question we'll do again. But this time Miller indices is not given to us, we need to find them. This is different from the question number 2. Okay, let me fix my camera. I think it's getting very blurred. Yeah. So for the first case, let us say we are going for the black one. Okay, sorry, I not saw any comment. There was few comments. Okay, yeah. So let's start with the blue one first. Sorry, let's start with the black one first. We know for the black one, if I choose this particular to be this point to be the origin, this particular point to be the origin, it won't affect since it is not lying on the plane. Okay, so what we can see, this is a x. If I say this to be the x, or this to be the a, or this is a y direction and this is a z direction. Okay, so in this case, what we can say in the x direction, we can write 1 times of a. In the y direction, it is 1 times of b it is cutting and 1 times of c is cutting. So we can take the values 1, 1, 1. We can take the reciprocal of this 1, 1, 1 will come and this will keep them in the curly bracket. This round bracket, not curly bracket, this round bracket. So this is the Miller indices for the first one. Now for the second one, what we can see that in the second, that is a blue one, in the blue case, here this particular plane is passing to the origin. If I take this particular point to be the origin, it is passing through it, which I don't want to happen. I will select the point in such a way that the plane shouldn't pass to the origin. So I can take this particular point, which is not in the within the plane. I am taking this particular origin, and considering this particular thing to be the origin, this particular lattice point to be the origin, what we can say, this will be our z-axis, this will be our y-axis, and the front will be our, that is coming out of the paper, will be our x-axis. So let's try it. So in the x direction where it is cutting, in the x direction, that is along this particular direction, it is cutting at the minus of a. Considering this to be the origin, we have to go in the negative direction. Considering this to be the direction of a. Okay, I have to go in the negative, that is minus of 1. In the y direction, again I have to go, considering this to be the direction, what we can say, that minus of 1 direction I have to go by minus of 1 unit. Now in the z, this is our z. In the y, yeah, in the z where it will cut. Now we can see, I should have choose some other origin. Now we can see that this particular point, if I am extending in the z direction, this particular plane will also be extended in that particular manner, and it will cut our z in the upward side. We know that it is going to cut in the upward side because in the downward side it is deviating from it. Okay, it's going away from the axis. In the above side, it's going to the convert to the z axis. It's going toward the axis. Okay, so similar manner we can say that it will cut to the plus of z in the upward direction. Okay, now considering that, what we can see is that this is 1 1 minus of 1 minus of 1 and 1. We can take the reciprocal of it. I will get again minus of 1 1 minus of 1 and 1. I will write a bar to them. So this is another plane we have got. Okay, this is another plane, that is a blue plane we have got. This is a blue one, and this one is a black one. So now let's see, what our first part is over, right? So now let's get to the second part. What second part of the question is telling us? We need to find the Miller indices of the line of intersection of these two planes. So we got the two plane. Now we need to find the line of intersection, how it is lying. Okay, We need to solve them by the geometric and the algebraic method. We know what is the algebraic method we are having. First, before going to the geometric method, let's try with the algebraic one. Okay, so we need to find the line of intersection. We know that we can use the Weiss Zone Law to find the line of intersection. That is a line, the line of intersection of the two plane will be the line in such a manner that it will be within two plane, right? If this is one plane and this is another plane, let us say, their line of intersection will lie in both of the planes, that is in plane 1 also and in plane 2 also. And Weiss Zone Law tells us that gives us the condition whether for the plane HKL and the UVW direction, HKL plane and UVW direction. It gives us the condition that under what condition the direction will lie onto the plane. So if it is satisfy the U times of H plus V times of K plus W times of L equal to 0. If it satisfy this particular condition, we can say that this particular direction, the UVW will lie in HKL plane, right? And so, why not the x-axis last H? Sorry, I not saw the comment, but yeah, let's go with the. Okay, so you are asking about this particular thing. So why not the x-axis last H? Sorry, I not got your
Hello.
question. I think you are talking about this particular question only, but
Yeah.
yeah, can you clarify? Like, if you are able to unmute yourself, then that will be really great because I'm not able to
Hello.
understand the question.
Hello.
Okay. So meanwhile, what we'll do, we'll proceed with this particular question. Okay. Okay. So this was the condition for the Weiss Zone law. Okay. So now what we can see that we got the two planes previously only. We what we need to find, we need to find the direction, that is the line of intersection. Okay. So this particular line of having the particular direction of UVW and the Miller indices, under what condition it will lie onto the plane 1 1 1 and minus of 1, minus of 1 and 1. This is the one which we need to find. Okay, these are the planes given to us which we find right now, and we need to find U V W. Okay, so let's apply this particular equation, this particular Weiss Zone law, and this is the H, K and L. For the 1 1 1 plane, if we apply, that is the HKL will be 1 only, so we'll get U plus V plus W will be equal to 0. For the 1 bar and 1, this particular plane, we can say that the minus of U minus of V plus of W will be equal to 0. Right? So now let's add them. If we add them, what we'll get, that is the U will be cancelled out with each other. V will also be cancelled out, V and minus V. We'll get the 2 of W will be equal to 0. And W is equal to the 0. Let's apply this particular equation W equal to 0 onto the any one of them, that is a U plus V plus W equal to 0. So what will, let's apply in the first one, U plus V plus W is equal to the 0. W is equal to 0, that means the U plus V will also be equal to 0, right? So what we will get, U will be equal to the nothing but minus of V. Okay, so what, so U over V will be equal to the minus of 1 over 1. And therefore, what we can write, we can See, this will be always, if we want one, you will say that u and v, I exactly someone want to find u and v, then it will be nothing but minus of 1 times some factor, and v will be minus of 1 times some factor, but we are not interested in the factor. Let's write down what we are getting: u as minus of 1 lambda, v as minus of 1 lambda, and w to be 0, this particular directions. And we know when we talk about the directions, we go we cut the, sorry, not 1, this will be u, v will be plus of 1, pardon me. Yeah, that's right, it will be plus of v. And so what we need to do, now we can simplify it. We'll divide entire thing by the lambda, we'll get minus of 1, we'll get the answer to be the minus of 1, 1 and 0. So this is the direction which we are getting. So this direction, this particular line will lie in our plane according to the Weiss Zone law, and this is the correct answer. Okay. So our one of the part, the one of the question, that is we have to find it by algebraic method, that is the Weiss Zone law. Using Weiss Zone law, we have found it. Now, what about the geometric method? In order for us to do that, we need to find this. We need to find the 2 points where they are intersecting. So we can see that this particular plane, blue, and the black one are intersecting at this particular point. And also they are intersecting at this particular point. Right? So what we can say, it will be this particular direction will lie, will be in the, this particular will be the line of intersection. We know that this direction is nothing but this direction. That vectors are the good thing about the most of the important thing about the vector is we can translate them. And this plane, this particular direction is, and this particular direction, both are equal with each other. Sorry, both are same. If we find the direction of this, let us say considering this to be the origin, no, we will consider, when we find the mirror indices for the direction, we will consider the origin on one of them, and this will be our x-axis in this case. Sorry, in the a direction will be this is will be our b direction, and this will be our c direction. Okay, so from this what we can say, in the positive direction we are going the x, that is a +1. Over here we'll go over here, and then we'll go to the this particular point. So in the x we are going by +1, in the y we are going by minus of 1 and 0, and now what we'll get, 1 1 bar 0. Did we got something different when we did last time? See, here we got what we got answer, 1 bar 1 0. But the question which we should ask, that are these two are different from each other? No, they are exactly same. So negative of this will be this. So line of intersection is this also and this particular. Okay, and that's how we can find. So we did the particular question, we find the Miller indices of both the planes, and we also find the directions, the line of intersections. Okay, and that's how we solve the question number 3. If there is any doubt, please let me know. Okay, meanwhile we can proceed to the question number 4. This particular question. So now the question is telling us, pardon, yeah. So now the question is asking us that write the zone equation for 2 to 1 zone. Okay, 2 to 1. I will just have a water. So here what is given, that is we have to write zone equation for 2 to 1. focus on the bracket that has been used. Bracket is in the square. So we know this is nothing, this is not a plane, this is a direction. And since the square bracket has been used, not this particular pointed bracket, so we can say that this is nothing but a one direction. This is not a family of direction. Okay, so now the question is asking us to draw the to write a zone equation. What is a zone equation? We just read it, right? We just know that what is a zone equation. That is a h times u plus k times v plus L times W will be equal to 0. This is nothing but a zone equation. So we know the U, what we know over here among HKL and UVW, we know this is a direction, that is a U, V and W we know. We can substitute those value over here. So what we'll write, it will be the 2 times of H. V is nothing but 2. So 2 times of K plus W is 1, that is, it will be 1, so L. So this is our zone equation. This is our zone equation. So the question told us that is a 2 to 1 is a direction. This zone direction, there is a zone axis is given to us. We need to write the equation. So now this is a zone equation. So all those planes which satisfy, that is a HKL, there is a set of the planes HKL which satisfy this particular equation. We can say that those will undergo the diffractions. We are not going in the depth of this particular diffraction part with respect to the zone axis since it was not covered in the syllabus yet. Okay, so the first part has been covered. That is what is write the equation of the, we have to write the zone equation. So now let's move to the second part of the question. Second part of the question is asking us that which of this plane. So we have planes HK. Which of these planes that is belong to the 2 to 1 zone. So we write the zone equation for 2 to 1, and that is this is the one. Now what we need to find that which of this particular set of the planes will lie in the, will satisfy this particular zone axis. Which of this belong to this particular zone means which of the planes is satisfying this zone equation. So all we need to do over here is that let us select the first one, 1 bar 0. This is a plane. All we need to do over here is substitute this particular HKL, this particular set of plane in the zone equation. Let's do it. So what we can say, H is 1, so 2 times of 1 plus 2 times of is minus of 1 plus L, that is L is 0, 0. And whether it is equal to 0 or not, that is something which we need to find. That is a equation is satisfied only when the LHS is equal to the RHS. So let's try to solve it. We will get 2 over here, we'll get minus of 2 over here, multiplying this to plus of 0. Now we can see that they are cancelled out with each other and we are left with 0. So that is the plane number 1, 1 bar 0. This particular plane satisfy the zone equation. So that is this particular plane belong to the 2 to 1 zones. Okay, in the similar manner we can solve other set of plane also. That is a 1 bar 1 3, 0 1 bar 2, 1 3 bar 2, 2 bar 2 1. Let's try. Let me try one more. I will solve 1 3 bar 2 again. Okay. So now in this case what we are having, HKL is nothing but HKL is given to us 1 3 bar and 2. So this is H, K and L. Let's substitute that in this particular zone equation which we found out, sorry, over here. So 2 times of H, that is 1, 2 times of K, pardon me, 2 times of K, that is minus of 3, plus L, L is 2. We need to find whether this summation, this particular equation after solving gets 0 or not. So 2 ones are 2 plus, not plus, minus. So minus of 2 3s are 6 and plus of 2. what we can see over here is 2 to 4 minus of 6, that is minus of 2. So it is not equal to 0. So this particular plane 1 3 bar 2 does not belong to the 2 to 1 zone axis, and that's how we can solve all these types of questions. Okay, and with that we solve the question number 4. If you have any doubt, please let me know in the comment section, or you can unmute yourself. Now, in meanwhile, if there is no doubt, we can proceed to the question number 5. Question number 5 is on the reciprocal lattice. Okay, it's a good question. What we want here, we need to show that the volume of the reciprocal unit cell. We have the reciprocal unit cell. What is the volume of the, we need to find the relation between the volume of the reciprocal unit cell and with the volume of the direct space unit cell. Okay, let me write what something which we are going to use over here. Okay, okay, let's start with the particular thing. What is the volume of the reciprocal unit cell? We need to find the volume of the reciprocal unit cell. Okay, we know it will be nothing but A cross A star, B star, and C stars box product, scalar triple product of A star, B star, and C star, right? And this is the volume of the reciprocal unit cell will be given by this particular box product. What we need to know, that is what does the box product mean? A star cross B star cross product of this with the dot product of this. This is what it means. What other things which we know is that the A star is equal to the, this all are vectors. Okay, I'm not writing, but still they are vectors. A star is nothing but B vector cross of C vector divided by, pardon, I shouldn't write the, this is wrong. A star will be equal to the B cross C divided by volume. Okay, all the, like, you might be thinking that we can write the other way also, like that is a B will be equal, that is a will be equal to the B star cross C star. That is also true. So reverse is also true, we can write in this manner also. So A star we have wrote. Similar manner, we need to find the B star also. So B star will be nothing but C vector C cross A divided by volume. And the C star will be equal to the A cross B divided by volume. Okay, and that's how it is. So now what we need to do, we got the A star value, B star value, and we got the C star value. What we will do, we'll just substitute in this particular equation, A star, B star, and C star. Let's try to do it. We can write A star as B cross C divided by V cross of this with the B star. B star is C cross A by V. Okay. Now a dot product of all of this with the C star, and we know what is C star. C star is A cross B dot V. A cross B divided by V. Now we need to solve this. Look like complicated, but it is not. It's very easy. Let's take the another fresh page. See, one of the property of the cross products. Let's write one of them. that is A cross B cross C will be nothing but A dot B, A dot C, that is a dot product of these two, times B vector. Let's write vector on all of them. Since I started, I will write all of them. Minus, now dot product of B and C. Okay, so B dot C times of A. Okay, this is the one. Same thing, this particular system which we got it over here will apply to the formula, the equation which we got to the last time. So let us write the V star volume from the previous equation that which we found out. It was B cross C by V, C cross A by V, and A cross B by V, and here is cross, here it is dot. So I will just write same as it over here. So we got B cross C divided by V cross product of C cross A divided by V dot product of A cross B divided by V. So now we can see, we can consider one of them to be our vector A. Okay, sorry, I not forgot to write bracket. It's okay. So now this is, we can consider this to be the A and this to be the B and C. This is B and this is C. Let's apply our formula. No, instead of doing like that, what we can do, let us say this is our A. A is represented by B, B is represented by this, and C is represented by this, all of them. Okay, and now we can apply this particular equations. So it will be A dot C, that is the dot product of last two things, that is a B and C. B and B, and the last one is nothing but a dot product of C cross A. Minus, dot product of this, dot product of A and C we have applied, times B, that is this is over, that is A dot C is over, and we have to write B. In our case, B is nothing but C. Okay, now we are applying the same formula, okay, on this particular equation. Now we need to do B dot C, that is a dot product of these two things, C dot product of C cross A times B vector, A vector, that is a B. This entire thing will be in the dot product with this. Don't forget the volume. Since volume is nothing but a scalar quantity, we can club all of them and we can write the V cube. And so what we can do, and what is remaining over here, A cross B. Okay, let's move ahead. Now what we can see, that this will be, I can write B dot C as a box product in this particular case, B C A, and C vector minus C cross A will be perpendicular to the C, and vector which is perpendicular to C, we are taking the dot product with C. So it will be nothing but the angle between them is 90, and the dot product, that is cos of 90, is 0. This entire term will be gone, and so this entire thing is gone. Now what we are left with is we have to do the dot product with there is a dot product A cross B divided by V cube. Box product is the property is that we can change their variable in the sequential manner. So I can bring A first, then B, and then C. Right? I can just move them. Here what we can see is that this is a vector. This is a scalar quantity now. It is associated with the C vector. Now what we can do, C dot AB, that is we can write again the box product C, A and B. Okay, and again we can move in the sequential manner and we can say that we'll get the A, B and C again divided by VQ. So what we'll get over here, that is a V star, that is the volume of the reciprocal lattice will be equal to this is nothing but ABC is the volume of the real lattice. This can also be written in the ABC manner and this is also be the volume and divided by VQ. So we can write, they will be cancelled out with each other, we can write this one upon V. So V star, that is the volume of the unit cell which is associated with the reciprocal lattice, and the volume of the unit cell which is associated with the real lattice, they will be equal with each other. And that is how we can solve this entire questions. Okay, with that our this particular question, the question number 5, that we need to show that the volume of the reciprocal unit cell is the inverse of the volume of the directive space unit cell. Okay, and the question number 5 is done. Now if you have any question regarding this question number 5, please let me know in the comment box. Meanwhile, if there is not, we can move to the question number 6. Okay, since there is no doubt, we can move ahead to the question number 6. I think it's not very good in the visible manner. So let me explain the question, what it is written, and
Yeah.
I will read it also. Yeah, I think now it's quite better. Now the question is that we have to compute the Cartesian coordinate system of a lattice point compute the Cartesian coordinate. We need to find the coordinate with respect to the Cartesian system. Of a lattice point, we are given the lattice point, it is a 2, 3, 1. Okay, of the orthogonal lattice. Okay, so we have the orthogonal. And the point is given, that is a lattice point, that is a 2, 3 and 1 is given to us. And we need to find this particular thing, this particular coordinate in the, this is given in the orthogonal lattice system, right? We need to find the Cartesian. We need to find that in the Cartesian. How we can do? It's not very complicated. It's very simple. Another few more information is given, so let's consider that information also. So here the lattice parameters are given to us, that is a 1 by 2, 1, 2, 90, 90 and 90. The first three are the length, remaining are the angles. Since it is orthogonal, we already know that the angles will be 90, even though they didn't have given us to us this particular information, it would have been still be fine. Now what we need to do, let's draw orthogonal system. Let's mark the basis vector. Let us say that this is A basis vector, this is a B and this is a C. If I try to superimpose the Cartesian over here, again it will be like in the same direction only. It will be nothing but let us say over here it will be Ex cap, it will be the Ey cap in the same direction, because in the orthogonal they itself is the perpendicular with each other. In the C, Ez cap. Okay, so if you want to convert from the orthogonal to the Cartesian, what will be its coordinate transformation matrix? Here we need to write A, B and C, Ex, Ey and Ez. Okay, can I write Ex in terms of A? So A in terms of Ex, we can say that the A vector will be nothing but A times Ex cap. So what over here we got? It is nothing but A. Remaining, what about Ey cap and Ez cap? They are nothing but a 0. So we can write over here that it will be 1. Sorry, it will be A 0 0. So there is no component of A along the Ey direction. There is no component of A in the Ez direction. In the similar manner, we can say that for the B also there will be no component in the Ex direction, that it will be 0. And in the B direction, sorry, in the Y direction, which is along the B, it will be nothing but B. And in the Z direction, it will be 0. In the similar manner, it will be 0, 0 and C. So this is what we got the coordinate transformation matrix. Now it's very easy. We need to find like what this particular coordinate transformation matrix will do. What this will do, this will convert our old coordinate to the new coordinate. The old coordinate is associated with the ABC and the new coordinate is associated with the Ex, Ey, Ez. That is nothing but a Cartesian coordinate. Let's substitute the ABC value and try to find the values. Pardon, it got little bit lag. Yeah. Okay. So the point which we were having was we need to, that is a 2, 3, 1. This particular point we need to, I shouldn't use the bracket. It's 2, 3 and 1. This is the given in the Cartesian, sorry, this is given in the orthonormal coordinate system. We need to write in the Cartesian coordinate system. Value of A, B, C, that is a lattice parameters was 1 by 2. I think the remaining was 1 and 2. Yeah, it is 1 and 2. B is 1 and C is 2. And we found the coordinate transformation matrix. A is 1 by 2. Remaining part was 0. B is 0. Sorry, B part will be 0, 1, 0. And C will be 0, 0, 2. We just substituted the value of A, B, C over here. Now we need to find the new coordinates of the point which is 2, 3, 1 in the orthonormal unit cell. It will be very easy. All we need to do, we need to take a product of them. Okay. Matrix multiplication 1 by 2, 0, 0, 2, 3, 1. 1 by 2 we multiply with 2. Remaining thing will be 0. Right. So if I write first case, that is a 1 by 2 multiplied by 2 and remaining are 0 plus 0. This will be the first. Second, 0 multiplied by 2, I will get 0 again. 1 multiplied by 3, it will be 3 and 0. Remaining will be 0 plus 0. 0 multiplied by 2 will be 0. 0 with 3 is 0. 2 with 1 is 2. So what we can say, that is, let us say this will be the x, y and z in the Cartesian coordinate system, and this was in the orthonormal coordinate system. So we can say that x, y and z in the Cartesian coordinate, we can write to be the 1 by 2, this will be cut and we will get 1. We'll get 3 over here and we'll get 2 over here. So what we got, 1, 3 and 2. And this is the lattice points, sorry, this is the point 1, 3 and 2 which was 2, 3 and 1 in the orthonormal system. Okay, great. With that we are able to solve question number 6. So question number 6 is over. See, in this type of questions, when we need to transform from the one, we need to transform one lattice point or one vector or one lattice point from one coordinate system, that is in our case, in this particular case, orthogonal is given. If we need to transform orthogonal to the crystal, that is a Cartesian coordinate, sorry, not crystal, to the Cartesian coordinate, all we need to do, the only effort which we need to make is to find this particular thing. That is a coordinate transformation matrix. So this coordinate transformation matrix will convert, this coordinate transformation matrix will convert the old coordinates, which is corresponding to the old basis vector ABC, to the new basis vector, which is x, ex, ey, and ez. That's how it is. The question can be even complicated in this particular cases when let us say that you need to you need to transform from non-primitive, that is a FCC, face-centered cubic, we know it is a non-primitive in nature, but dealing with the sometime in some certain cases we require the primitive unit cell, usually when we work in the reciprocal lattice system. Okay, so we need to find the primitive unit cell in that particular case. Again, all effort is been needed to find this coordinate transformation matrix to convert from the non-primitive to the primitive. If you know how you can find the coordinate transformation matrix, the question is solved. Okay, okay, yeah. So with that, our question number 6 is over. Let's move ahead. If there is any doubt, please let me know in the comment section and we can discuss it. Yeah, here now the question already came, which we were discussing about. It might not be visible perfectly, so let me explain the question. Yeah, now it is. The question is telling us that the find coordinate transformation matrix for conversion of the conventional FCC unit cell to a primitive unit cell. Okay, so what we need to do, FCC is given. In the FCC, what conventional unit cell, we know conventional unit cell how it is. Let's draw one conventional unit cell in the FCC. Let's mark the points, lattice points, all at the corners, and at the face center also it will be there. In all the face center it will be there. On the front face also and the back face also. So overall we will have effective 4 lattice point to the unit cell, and since this number of lattice point is more than 1, this is non-primitive. Our question is demanding us that convert non-primitive unit cell to the primitive unit cell. Okay, this is what our question is asking us to do. Okay, so first let's find geometrically, let's find where the primitive unit cell is lying in the case of face-centered unit cell. Okay, for that, see there are few additional information is given that find the coordinate. We need to find, not only we need to find the coordinate transformation matrix, not only we need to find the coordinate transformation, we also need to convert one of the point which is in the non-primitive unit cell, conventional unit cell, to the primitive unit cell. Okay, we'll do this part first. Let's focus on the first part only, that is a coordinate transformation. For this, let me draw a unit cell first, FCC, face-centered unit cell. Current task is to find the is to locate is to visualize the primitive unit cell within the conventional unit cell of FCC. Okay, let's look at the lattice points. These are the lattice points. It's not completed yet. It will be at the face center, all of them, on the backs also. Okay, let me know. I'm not drawing all, so for our simplification, okay. Let's now, this is a FCC unit cell. Let's visualize the non-primitive unit cell in this. If I draw this particular, if I connect this particular lattice point, considering this to be the origin, to all the face centered one, this three, bottom one, side, and the back one, what I will get? This is what I will get. Similarly, from the top, like just opposite to this, that is 111 point from the origin. If I connect with the front, this side, front, top, and the front one, if I connect them, and the front face, let us say over here, front is over here, let us say for a time being. This is how it is. This two. Now we can connect them, and that this will be our non-primitive unit. Sorry, primitive unit cell. All the points will be connected with each other, and we can find our primitive unit cell. It's really difficult to draw, but yeah, one can do it. So if you draw it now properly, you will get it like this. So this three and this three. Effectively, how many points we need? We need total of 8 points to form the unit cell. To form any unit cell, we need 8 points. This was a 2 point. That is the corner of the FCCs. Okay, 0, 0, 0, 1, 1, 1 point. Remaining 3 points we took from the faces. Since we know there are the 6 faces, if I join them with this 2 point, effectively there will be the 8 point. And those 8 points will form the primitive unit cell. So for the time being, we got to know that how we can find the primitive unit cell. Now, our next task is to find the basis vector. We need to find our initial, that is A, B, and C. In terms of the, let us say our primitive will be A prime, B prime, and C prime. So we need to find A prime, B prime, and C prime, and ABC, their relation in between them. Okay. So now let's go. Let's now only visualize this black part, this black dotted one. Okay, that is we are connecting this. Considering this to be the A axis, considering this to be the B axis, and this to be the C axis. Our Cartesian coordinate will also coincide over here only, in the same manner. See, for the cubic, tetragonal, and orthorhombic, in all these cases, our Cartesian coordinate system and the crystallographic coordinate system will coincide with each other. So we can say that the EY will also be over here. EX will be over here, and E Z will be in this particular direction. Okay, now let's focus on this particular one, this particular direction, which we mark that this will be the one of the basis vector for the primitive unit cell. We need to find it. So how I can find it will be nothing but if I use 0, this to be the origin, this direction, how we can find that? I have to go by a unit amount of, so not unit, half amount of A and the half amount of B. So I can write this particular A prime to be as half of A plus half of B, right? Instead of using A and B, let's use the, okay, let's use A and B only. This is how we have got that A prime is nothing but 1 by 2A, 1 by 2B and 0 times of C. In the similar manner, one can say that the B prime that is this particular thing, one can find it, it will be 1 by 2B plus 1 by 2C. See, I am writing A prime, this to be the A prime, but in the crystallography people consider this to be the C prime. It's all up to them, or they can consider anything. So this will be the C prime, A and B it will contain, and this will be the nothing but A prime, it will contain B and C. And then we will have one more, that is a B prime, it will contain 1 by 2 of A plus 1 by 2 of C. Okay, so now the formulas which we, the equations which we wrote, let's write them again. So we can write A prime is equal to the 1 by 2 of A plus 1 by 2 of B. B prime, sorry, it will be the C. A should not contain B and C. B prime will be equal to the 1 by 2 of A plus 1 by 2 of C. And C prime will contain 1 by 2 of B plus 1 by 2 of. This is how it is. Till now we have found it. Just a minute, I will have a water. Yeah. So now what we need to do, we need to find the A, B and C. Our next task is to find A, B and C in terms of A prime, B prime and C prime. Okay. We have the equations, we have three equations. We need to find A, B and C in terms of A prime, B prime, C prime. It's easily can be done. Three equations, we can solve them. So now what we can do, let's find out, let us take this particular one. This should be A. C prime should contain C. So now we can find the A from here. So it will be equal to the B prime minus of 1 by 2 times of C. It will be equal to the 1 by 2 times of A. We can write 2 times of B prime is minus of 1 by 2, sorry, minus of C. It will be equal to the A. C we can find, we have to find the C value. Okay, so from here, from A prime and B prime, we can find the, let's find C. So we should subtract something which should give me C only. So this content B and A, this content C should contain in A and B. Yeah. this contains C, this contains C, and this one. Okay, let's find C. So we can first of all let us add all of them. So what we'll get, A prime plus B prime plus C prime, all of them we have added. 1 by 2C will plus 1 by 2C will give us C. 1 by 2B, 1 by 2B will give us B, and similarly we get, okay. And so in this manner what we can see that we are able to, I think there is something is wrong, it's messed up. Let's try it again. A prime is equal to the 1 by 2 times of B plus 1 by 2 times of C. B prime is equal to the 1 by 2 times of A plus 1 by 2 times of C. And C prime is equal to the 1 by 2 times of A plus 1 by 2 times of B. We need to find A, B and C in terms of A prime, B prime and C prime. Okay, so let's add all of them. I will get A prime plus B prime plus C prime will be equal to the A plus B plus C. Okay, so from here what I can say, now let us take C dash. So we can write 2 times of C dash, which will be equal to the A plus B. And I know A plus B is nothing but A prime B prime plus C prime minus of C. So I can, from these two equations, I can write them as the 2 times of C prime, that is this, it will be equal to the A plus B. I can write from here, it is a A prime plus B prime minus of, sorry, plus of C prime minus of C. So from here I can find C. C will be equal to the A prime plus B prime minus of C prime. Okay, so here we can see that in the case of C, the C part is negative, remaining 2 are positive. In the similar manner, we can write B to be the A prime plus C prime minus of B prime, and A we can write that is a B prime plus of C prime minus of A prime, and that's how it is, and this is all. Okay, so what we need to find, the coordinate transformation matrix, right? We need to find A, B and C in terms of A prime, B prime, C prime. We have already done it. We'll just write. So for A, with respect to the A prime, we know it is minus of 1 is associated with them. And for the A with a B prime, we know it is 1. And for A with the C prime, it is 1. So similar manner, doing that, we will get 1, minus of 1, 1. For the C, we'll get 1, 1, minus of 1. And this is our coordinate transformation matrix. Right? Now what this coordinate transformation matrix is doing, it is converting conventional FCC unit cell to the primitive FCC unit cell, primitive cell. Okay, so the conventional which was not primitive, consisting of the 4 lattice point, it is converting to the primitive. Okay, so now this first part of our question number 7 is over. Yeah, this question number 7 is over. What is the second part is telling that we have to find the coordinate of 1, 1 by 2, 1 by 2, that is a 1, 1 by 2, 1 by 2. It was given in the non-primitive, that is a conventional unit cell. We need to find its coordinate in the new, that is a primitive unit cell. Let us say this is a primitive unit cell. We have the coordinate transformation matrix with us, we just find out, right? And we have the old one, that is a 1, 1 by 2 and 1 by 2 with us. We knew that this is minus of 1, 1, 1, 1 minus of 1, 1, 1, 1 minus of 1. Simple matrix multiplication. It will give us the new coordinate, that is a x, y and z associated with this. Let's try it. Let's do it right now. Minus 1 multiplied by 1, it will be minus of 1. 1, 1 by 2, 1 by 2 with a plus sign. 1, 1 by 2 is nothing but again 1 by 2 with a plus sign. We can go with another one. 1 will give us 1 only. 1 minus of 1 it will give us minus of 1 by 2. 1 and 1 by 2 will give us plus of 1 by 2. Okay, and 1 again we can solve for that. It will be 1 plus of 1 by 2 minus of 1 by 2. Okay, now let's solve it. It will be minus of 1 and this both will be 1. Cancel out, it will be 0. Here we can say 1 minus 1 by 2 plus 1 by 2. It will give us 1. And here this will cut out. Again it will give us 1. So this was the coordinate 0, 1, 1 associated with the primitive unit cell. Okay. See, now we can see that in the old coordinate system, which is 1, 1 by 2 and 1 by 2, the coordinate of the point was 1, 1 by 2 and 1 by 2. We converted it to the primitive and we got 0, 1, 1. All of them are, none of them are fractions. And that is a beauty of the primitive unit cell. Okay. This is mostly used in the reciprocal lattice when if you want to find the reciprocal lattice of a particular unit cell, then first you need to convert it to the primitive unit cell, whether it's FCC or BCC. In both of the cases, first you will convert it to the primitive unit cell, and then from there you can find the reciprocal lattice. So all the diffraction criteria and all, this is the thing which we have used. Primitive unit cell, the coordinate associated with them, because they are non-fractional in nature. Pardon me for that. Yeah. So with that, our question number 7 has been solved. If you have any doubt, please feel free to ask me, or else we can go to the next question. Okay, we are not going with the question number 8 and question number 9. They are quite lengthy, and considering our limited time to us, we'll start with the reciprocal lattice for the cubic. Question number 10. Question number 8 and 9 was quite lengthy, and the question was also, the doubt was also was not asked with respect to this particular thing. So we are moving to the question number 10. I hope it's visible. Let me focus it properly. Yeah. So the question number 10 is telling us something, that we need to find the reciprocal lattice for the cubic closed pack, FCC. Cubic closed pack, that is FCC. Okay, this is what we need to do. How can we do that? We need to find the reciprocal lattice of FCC. Okay. Reciprocal lattice. What does it mean? We need to find the reciprocal lattice. That is, we need to find the A star, B star, and C star. That is a vector of them. That is all we need to find. Yeah. So if we need to find A star, B star, and C star, for that we know that we need A, B, and C. This A, B, and C should be in such a manner, this A, B, and should be in such a manner that they belong to the primitive. You cannot take the conventional unit cells of FCC and apply the reciprocal lattice over here onto it. So for that we need to find A, B, and C, and with respect to the primitive unit cell, which we have already did, right? In the question number 7 only, we found it out. Let me show it to you. Where it went. Okay. Yeah, here it is. A dash, B dash, and C dash, they were nothing, they were associated with the reciprocal, sorry, they were associated with the primitive unit cell of FCC. And so we have found out A dash, B dash, and C dash. Let's write it down. So we found A dash. Let's now I will call it to be the dash only, since I am using dash. So I will call it. So we can say that the A dash is nothing but 1 by 2 times of, here I, instead of writing B, I will write EY cap. Considering B to be the, since it is a cubic, I can consider A, B, C all will be equal and their magnitude will be 1. Now EY plus 1 by 2 times EZ cap. Now similar manner we can say that the B dash will be equal to the 1 by 2 times of EX cap plus of 1 by 2 times of EY cap. Sorry, pardon me, EZ cap. And C prime will be equal to the 1 by 2 times of EX cap plus 1 by 2 times of EY cap. We got A prime, B prime, C prime. We need to find A star, B star and C star. How we can do that? We know that A star is equal to the B cross C. Here we are using prime, so we'll use prime. This divided by volume. Volume is also we can write. Oh my god. Okay, B prime cross C prime divided by box product. Volume is box product of A prime, B prime and C prime. It is nothing. It's just a mathematical thing we need to do. We need to write the cross product of B cross C, and we need to write the A prime, B prime and C prime, their dot product with each other. We can do it. We can easily do it. Once we find the A star, you will start seeing some pattern. Like how A star is that? We just need to find A star remaining B star and C star. Reciprocal lattice, that is B star and C star. We can find by the pattern, which is we will get in the A star. Let's try to do it. Let me take the another page. Okay. So now we need to find, first thing which we need to find over here is that B cross C. And we know with the B, there is no EY cap is associated. Only 1 by 2x and 1 by 2 EY. So let us write I. Let us write EX, EY and EZ. And we know if we want to find B cross C, so for the B, we know EX is 1 by 2, EY is 0 and EZ is 1 by 2. For the C, it will be 1 by 2, 1 by 2 and 0. We need to find the cross product of this. This multiplied by is 0 minus of 1 by 4. For the EY, 1 by 2 and this will be 0. That is a plus of 1 by 4. For EZ, it is 1 by 4. This multiplied by this remaining is 0 only. So B cross C we got. Right. So B cross C was minus of EX by 4 plus of EY by 4 plus of EZ divided by 4. Right. Next task is that we need to find the box product A, B, C, prime of them. Prime I am using only for the primitive. Okay. If I will use A, B, C, usually people consider that to be the conventional unit cell. They use for the conventional unit cell. Okay. So now let's try to find it. So we already find the B cross C. So I will write box product in this manner. That is a dot product B cross C. B cross C we got. That is nothing but A prime we also have. That is a 1 by 2 times of EY plus 1 by 2 times of EZ. And B cross C we got over here. That is a minus of 1 by 4 times EX minus plus 1 by 4 times EY plus 1 by 4 times EZ. So EX by 4 negative plus EY by 4 it is in positive and EZ by 4 it is also in positive. Dot product is very easy. So now there is no EX term over here, so this term will be already cancelled out. EY will get 1 by 2, 1 by 2 that is 1 by 4. Sorry, 1 by 2, 1 by 4 will be 1 by 8. This will be multiplied with this. Now 1 by 2 of EY and 1 by 4 of EZ, again we will get 1 by 8. We'll add them, we'll get the volume to be the 1 by 4 only. So we got the volume. So now let's write that. Let's write A star. A star, which we were saying that B cross C divided by V. B cross C we have got. B cross C is this only. Ex by 4 minus plus Ey by 4 plus Ez cap by 4. The whole divided by volume, that is 1 by 4. Okay. So I can write volume to be the 1 by 4 divided by 1 by 4. So this will be cancelled out. So what we got? A star we have got that minus of Ex plus of Ey plus of Ez. Note that I am only doing this for the cubic unit cell. In the case of non-cubic unit cell, you will get something else. Okay. So now Ex, Ey and Ez. So A star, Ex term is negative, remaining are positive. In the similar manner, B star we can write that will be, this will be positive, this will be negative, and this will be positive. And the same similar manner we got C star also we will get. So we got the pattern that in A star, Ex term is negative, remaining are the positive. Right? And that's how we have done it. So this is how we have find the A star, B star, and C star values. And with that, reciprocal lattices, the question with respect to reciprocal lattice has been covered. Okay. So question number 10 is already over. So now with that, our in total, even though I'm writing 10 over here, we have solved 8 questions. And those 8 questions are sufficient for you guys to complete the assignments. Okay, the assignment which is provided for the week 2, you can easily solve once you go through the 8 questions. Let us say in initial questions which I have discussed over here, you were not there, or you were not present, or you were missing due to some reason. The recording of this particular entire session will also be available on the YouTube, and the link of that will be shared to you using the SWAM portal. Okay, on your Gmail ID using which you have registered. So you can go through it, and it is very easy. And with that, our this today's session is over. Please let me know if you have any doubt. In the comment section, you can let me know. Okay, since there is no doubt, we can end this particular session.